Welcome fellow chemists to the third of many videos on the reactions of the alkenes. I hope you watched the second video on the addition of water because this one on the addition of alcohol is about 99% the same. First, let's take any old alkene and react it with alcohol. Nope, nothing is wrong with your screen. Nothing happens if you take an alkene and add an alcohol. Just like water, the alcohol is not acidic enough, so it holds on to its hydrogen so much that nothing happens. So once again, we turn to an acid to kickstart this reaction for us. After that, it is simply the addition of the entire alcohol molecule onto the alkene. Yet again, another piece of cake. I bet you are feeling a bit like Neo right now, but you need not worry about the impending arrival of Agent Smith. Neo may know Kung Fu, but you know electrophilic addition reactions. The first thing we need to get our reaction going is some electrophilic hydrogen. We know previously that an acid can promote the generation of them via the formation of H3O+. We do not have water, but we can generate a protonated alcohol. This will be our catalyst. One of the hydrogens from our protonated alcohol will add to the double bond. As we will be forming our carbocation intermediate as a result of this step, we want to form the most stable possible. A tertiary carbocation would be preferred, but in this case the best we can do is a secondary carbocation. We have generated the carbocation intermediate, so here comes the nucleophile. The alcohol has electrons to spare just like the water and halide did before. A pair of electrons on the oxygen is used to form a bond with the carbocation. Now the entire alcohol has been added to the molecule and we have a protonated ether. This is not going to stick around because a molecule of alcohol will remove the hydrogen from the protonated ether and regenerate the protonated alcohol, which was our catalyst from the very beginning. What remains is our product, an ether. If we had more or less already seen this mechanism before, then that means we have more or less already seen the regioselectivity before. Just as with the hydration video, there will be two potential products generated by the alkene and alcohol. For this first example, we can either produce 2-methoxypropane or 1-methoxypropane. I'm sure you recognize that the top product was the secondary one, and we would expect that to be the major with little if any primary one produced. Next up, we have 2-methylprop-1-ene, and the potential products here are a primary or tertiary ether. In this case, the product on the top, 2-methoxy-2-methylpropane, is tertiary, and thus we would expect that to be the major product of this reaction. Finally, we have 2-methylbute-2-ene. The potential products here are, like before, either tertiary or secondary. As we expect to produce a tertiary product most often if possible, the 2-methoxy-2-methylbutane product on the top is what we would expect to be the major product of this reaction. Hopefully by now you're feeling pretty confident in your understanding that this reaction and hydration are essentially the same, but if you're still a bit mystified, let me show you. I'm going to replace water and alcohol with HOX. First, the HOX is protonated, which generates our catalyst. Now an electrophilic hydrogen bonds to the alkene using a pair of electrons from the double bond. The carbocation intermediate is an electrophile, and the HOX has electrons to spare. A pair of electrons from the oxygen forms a bond with the carbocation, producing a protonated intermediate. Another HOX comes by, removes the proton, which regenerates the catalyst. So now we have an OX on the alkane. Change the X to a hydrogen, and we have produced an alcohol. Change the X to a CH3 or other alkyl group, and we have an ether. Like I said, these processes are the same. So just like the addition of water, the addition of alcohol is literally the addition of the alcohol across the double bond. It will only proceed in the presence of an acid. The acid promotes the formation of a protonated alcohol which supplies the electrophilic hydrogens. The hydrogen then adds to the sp2 carbon with a greater number of hydrogens. The carbocation is an electrophile, and the alcohol with the electrons on the oxygen is the nucleophile. An electron pair from the oxygen will form a bond with the carbocation, and the product that is produced then is a protonated ether. An alcohol molecule will remove the additional proton, which reforms the catalyst. The product is an ether, and we would expect a distribution favoring tertiary if possible, or secondary. The mechanisms for hydration and addition of alcohols are virtually identical. In the next video, we will discuss carbocation rearrangements. Thank you very much for watching. If you enjoyed this video, please like and subscribe as I have more in development. As we know how to form ethers from a reaction now, you might want to freshen up on naming these molecules if you have not already. As usual, feel free to get in touch with me via email, social media, or if you would like, make a request in the comments.